Thank you for giving me the great opportunity to talk here. My name is Toshiyuki Oda from CrossTas. I have participated to CASP 4 times. Two is from ICE in Japan, and last two is I attended privately. I think my colleagues and my colleagues and I got top rank in the category assembly category in CASP 12. I think. As I'm not good at English, especially listening and speaking, so you may better to ask me in the Discord or at poster or give me an email if you have a question. So I'll give a presentation from floor because I don't make presentation without my notes. Sorry. Can I close this window? Maybe. Okay, thank you. Currently, my affiliation is CrossTas, which is a company under Page Computing. I registered my affiliation as Infinite Creation, but the companies were merged this November, so I'm in CrossTas now. I think Page is much more famous than CrossTas or Infinite Creation because it was listed in top 500 or Green 500 in several times. Page and CrossTas are building. Okay. Page and CrossTas are building and running high-performance computing system. High-performance computing system. For CASP15, I use some supercomputers, which is Page and CrossTas were running. NJ1 was used for training. NJ1 is used for training AlphaFold 2 and AlphaFold Multimer, and Satsuki was running PGRAS. I'll address later. The Sakura was easy to use for me, and it's one of the computer I mainly use during the CASP season. And I use a general workstation. I call this ICWS for this CASP. So, as you know, that AlphaFold 2 and AlphaFold Multimer had made a breakthrough in protein structure prediction, and they have been provided in general licenses. So I thought the prediction by them would be the baseline of the CASP. So I set my challenges in this CASP as follows: collect a sufficient number of evolutionary related sequences for input, and improve the structure predicted by AlphaFold 2 and AlphaFold Multimer. There are several abbreviations and possibly ambiguous words, but I think you can understand them with context. My basic pipeline in CASP15 was like this. In summary, perform sequence similarity search, generate multiple sequence alignments, predict the structure with AF2 and AFM, and refine them and relax and submit. The process is semi-automatic. I could get predicted structures by just typing some simple commands. However, things did not go straight as the usual CASP. I made many manual interventions. I will address them later. To tackle the first issue, I use extra tools and databases in addition to those used in the original pipeline of AlphaFold 2 and AlphaFold Multimer for MS generation. PGRAS is an ultra-fast sequence similarity search tool developed by Page in collaboration with Riken and the National Institute of Genetics. It can search a terabyte scale database in about 20 minutes. Because it operates in parallel, there is no difference in search time up to about 10,000 amino acids. Cypress EXP is a customized version of Cypress, but it's basically the same as the normal Cypress. HH Blitz and Jack Hammer are used in the original pipeline. it runs in parallel. It runs in parallel to some extent, but it requires several hours per sequence. Jackhammer was used to construct an MSA from PGRAS and Cyberrust hits. After I got MSA, the next step would be MSA filtering and feature building. Since MSAs tend to be large, we could create variations of MSAs with several filtering criteria. And I made input features with some trick for multiple predictions. Dr. Yoshitaka Moriwaki or Dr. Min-Kyun Beck showed that a monomer version of AlphaFold 2 can use for multiple prediction. So I used Dr. Min-Kyun Beck's technique for adding extra gaps between the subunits. And several other techniques are implemented. F2 and FM's input features are roughly made with these steps. The data I made were inserted around here. The next step is structure prediction. The structure prediction was essentially the same as the original F2 and FM, but with some modifications. The number of recycling steps was larger than the original one, and it was changed considering the time and computational resources. So it produces around 1,000 to 2,000 structures in standard cases. The next step is model selection. For model selection, I use original IF2 and AFM confidence metrics. But for monomer, I use only PLDT rather than 70 because there might be disordered regions. For multiple prediction, it was the same as the original one. And I use TM score to keep the variation of the structure considering ensemble or alternative form or misprediction. After the selection was made, refinement was performed to tackle the second issue. For building a refiner, I utilized the codes and parameters provided by DeepMind. In other words, I fine-tuned AlphaFold multimers parameter provided by DeepMind for refinement. I use only primary sequences of queries and atom coordinates as input. It means it did not use MSAs or templates. And it was intended to model physically preferred structures. Let's explain what physically preferred means. When training a model for 3D structures, when training a model for 3D structure prediction of proteins, we should crop sequences because training needs more memory than inference. If I simply take amino acid according to the distance from center atom, it can produce segments floating in the air like this. I eliminated those ground truth candidates. When I select the ground truth, I use the structures composed of segments with a sufficient number of contacts with other segments. I implemented some other techniques, but we are preparing a paper, so please check it for the detail. The result was promising. X-axis indicates the Q of the input structures, and Y-axis indicates the Q of the refined structures. In many cases, though the effect was small, it could improve the input structures. The outliers came from the recycling step 0 or 1. The accuracy of the structures at the recycling step 0 or 1 were a bit lower than the others. I was focusing on the multimers, but I also checked the performance against monomer targets. The difference in TMS scores was so tiny that was less than 0.1. In this plot, X-axis indicates TM score of the input structures and X-axis indicates the TM score of the input structures and Y-axis indicates TM scores of the defined structures subtracted by those of input structures. Similar to the multimer targets, the effect was small but positive, but some targets had some score degradation. Possibly it was because they were partial region of much larger protein. Let's move to the section on visual inspection and manual intervention I made. I usually predicted structures using full-length sequences of all subunits, but many times the total number of amino acids was so large that I could not handle it with V100 GPU. In that case, I performed domain parsing and MSA cropping, or predicted the whole structure with CPU mode. The domain parsing step can be split into 4 steps. Firstly, I split sequences into fragments of lengths from 500 amino acids to 1000 amino acids and pick them up with a random guess. Or sometimes I utilize the results from domain prediction with SMART. And I predict the structures and visually inspect which regions or subunits were interacting. And I decided new boundaries so that I do not disturb the interfaces. After that, I predicted structure again. And concatenated them with simple scripts. I also performed whole structures, predictions, whole structures with CPU mode. However, the results were not so good. Not so good. In addition to the size of the targets, there are many difficulties in CASP15 targets. The semi-automatic pipeline sometimes produces highly scaled MSA depths like this. The x-axis indicates the position of the sequence, y-axis indicates MSA depth. In other words, the number of evolutionarily related sequences with an amino acid in that position. If the depth of the MSA was highly scaled, I kept sequences with amino acid in those thin regions and randomly removed other sequences to flatten the depth. When I thought the depth was not enough, I performed some additional searches to get more sequences around thin regions. Possibly it was a feature of my refiner. My refiner sometimes produced globular structures like this. Like this, and sometimes produce many atom crashes. I am investigating what is causing this problem. Anyway, I didn't use these structures, which I thought the refiner did not work well. And I should note that I checked the other group's prediction and I assessed whether my protocol was working well. In addition, there are many miscellaneous things. Let's see the results. This is the result of a single domain. In summary, I could submit acceptable. I mean, TM score higher than 0.5 predictions in 85 out of 93 targets. All means all predictions, including not submitted models. There were much better models. It means that there is room for improvement in our scoring and ranking system. And this is result for assembly targets. I did not have time to search and assign the interfaces, so this result is not confident so much, but there is large room for improvement in assembly prediction compared with monomer prediction. Then how about the challenges I set for CASP15? I investigated whether my X-house sequence similarity search worked well or not. In many of cases, I could find more than 1,000 evolutionary related sequences. this graph, x-axis means the number of corrected sequences, and y-axis means TM score of the best model without refined model. The dot indicates a single domain, so dots above the 1125 D1 is other domains of 1125. Amazingly, with less than 100 evolutionary sequences, AF2 or AFM could predict very accurate structures. T1113 is a free modeling target as hard as I know, but AlphaFold Multimer could predict accurate structure with 26 sequences. I analyzed the effect of filtering. The second column indicates the number of predicted structures which had top accuracy for a target. The third column indicates the number of models considered. Because of the computational resources, some filters were not used for some targets. And there are other factors I should consider, like the existence of templates and random sheets. So this result is preliminary. There is a big difference. There is a big difference between the non-filtered cases, feature input version and MSA insert version. I think the biggest difference between them is MSA prop size in the feature processing.py in official AFM script. This variable is infinite in future input version. So if you are interested in, please check this variable. So anyway, if I believe this table, no filtering tended to perform better, but variety of filters was needed to get maximal performance. I think T1160 and T1161 is from this filter. Next, I investigated how our refiner improved structures. X-axis means TM score of the input structures, and Y-axis represents TM score of the refined structures. The result looks nice. It was similar to the result of the test data set I showed before. The gain was small, but the effect was positive. The refiner worked very well. There were several targets for that I couldn't submit a good model compared with other groups. One is T1130. It was shown in the previous scatter plot. Yeah. With this target, I could find the evolutionary related sequences only from Magnify, but the identity was very low. So the hits were suspicious, and resulting models were not so good. So if I fed randomly placed atoms into our refiner, the refiner produced structures that looked somewhat good. It was like a de novo structure prediction. I used this technique for this target, but could not build a good model. It is surprising that young group get homologous sequences about this target, and it's surprising to the top group get such an accurate prediction. Yeah. And T1125 D1 is a similar case. There are only a few evolutionary related sequences which were almost identical or were possibly false positive. It's quite amazing. Other groups made good predictions too. And the third example is T1173. T1173 was a part of the longer sequence. So I added 196 amino acids on its M terminal. After building some structures, I found that bad prediction in C-terminal region compared with the collab-fold result. So I checked the depth of MSA and found highly scaled distributions. Therefore, I took the thin region and made the distribution flatter. And the resulting model looked nice, similar to that one from the collab-fold. However, the accuracy of our model was much lower than the top group. The problem is the N-terminal of domain 2. Possibly the depth of the MSA was not sufficient. I might have gotten better structures if I had selected more sequences around here. The best model with our semi-automatic pipeline without manual intervention showed better accuracy. And I made many miscellaneous mistakes. If there were no submission from the team 278, it would be just my mistake. So in conclusion, AlphaFold 2 and AlphaFold Marchma are amazing. It's surprising that I could predict such accurate structures in most of the cases. And machine power is essential. I couldn't show such a good performance without the help of high-performance computing systems that Peggy and Crosses are running. And my protocol worked well. It would be essential to create many models with large MSAs and various filtering criteria. At least for standard, AlphaFold 2 and AlphaFold Marchma pipeline. The effect of my refiner is small, but the effect of my refiner is small, but positive. And maybe so. And sorry, thank you very much. And there are still room for improvement. Better scoring and ranking systems are demanded to compare the result from different applications. And the prediction from single sequence and prediction of assembly structures are still challenging. I will learn from other groups. Finally, I want to thank all members of Peggy and Crostas for supporting my research, and National Institute of Genetics and Riken for supporting our metagenomic pipe project and PGRAS. I use many software and DBs in this CASP. I really thank all developers and maintainers who made these software and DBs available. And I thank collab-fold group and Elephone group for sharing their prediction during the season. Thank you very much. So as I said, I'm not so good at English, so I may answer this night if you send me a question via Discord or email. Thank you very much.
Thank you for sharing. Questions, please.